Hi everybody. In this lecture for Math 219, we'll speak about separable equations and homogeneous equations. In the first lecture, we had an introduction and we talked about some general qualities of differential equations. And we also saw direction fields, which was a way to understand solution curves without actually solving an equation. Now we want to get our hands on some special classes of first order equations. And the first of these, which we can explicitly solve, is separable equations. So I'll try to make a definition. So an equation of the form, or let me say an equation that can be written in the form dy dt equals a function of t divided by a function of y is called a separable equation. Okay, here we don't care too much about what m and n are. The important thing is that everything about t is separated from all the other things about y in a multiplicative fashion. Okay. Now, a non-example and an example. Something like this, dy dt equals t plus y. Although it looks quite simple, it is not separable. I mean, there's a t and y, but they are not separated multiplicatively. There's an addition between them, and you can convince yourself that there's no way to rewrite this equation as mt over ny, however complicated you choose m and n. But some equation like this one is separable. For actually obvious reasons, because you already have the functions mt equals 2t squared and ny equals y squared plus 1, so it's exactly of the desired form. Okay, now we have a clear-cut method to solve separable equations. So let me say solving separable equations. So let us start from dy dt equals mt over ny. Okay, what we do is multiply both sides of this equation by ny. And that brings us here. Ny times dy dt equals mt. Okay, so far so good. Now, integrate both sides with respect to t. Now, this may raise some eyebrows because, okay, so, well, it looks like this first of all. Well, the right-hand side is not a problem at a theoretical level. It's a function of t and you want to integrate it with respect to t. It might be an easy or difficult integral, but anyway, we can do something about it. The left-hand side, though, is, well, we have both y's and t's, so we don't want that, right? I mean, if we don't know y, we cannot integrate that with respect to t. However, there is something special going on here. You see a dt right here and a dt right here, so intuition tells us that we could maybe cancel them. And actually, that's a correct step. That's justified by chain rule. This integral is exactly equal to integral of ny dy. And now on the left, you don't have anything about t. That's good news, because then you can do the integrals on the left and on the right independently and get an equation. Integrate and work out the arithmetic. Okay. Let's see this on an example. Okay, let's say y prime is equal to 2x divided by y plus x squared times y. And let's add an initial condition to this problem. Let's say y0 is equal to minus 2. So, okay. Now, this equation is separable. Well, you can factorize y in denominator, and the x's are then multiplicatively separated from y's. Or you can say multiply both sides by y. So y prime is, remember, dy dx. So if you multiply both sides by y, this will look like y dy dx equals 2x divided by 1 plus x squared. Now it's much more clear that it's separable. Then integrate with respect to x. And for the reason we discussed before, the left-hand side simplifies to y dy, and the right-hand side is this integral. Okay, now it becomes a matter of whether or not we can find these integrals. In this case, they're rather straightforward. The left-hand side will give you y squared over 2. The right-hand side, you could make a simple substitution, u equals 1 plus x squared, and in that case, du will be 2x dx. So this is essentially du divided by u. So its integral then is natural logarithm, absolute value of u, plus a constant. I can hear you asking why I put a constant on the second integral but not on the first integral. That's fine, because if two functions are equal, their antiderivatives differ by a constant. Maybe a more pedantic way of doing this would be to put a plus c1 on the first integral, then a plus c2 on the second integral, and a subtract, and c2 minus c1 is the c shown, but that's not necessary. This is fine. Okay, then we can back substitute u. And I can also do this, multiply by 2, so it's 2 ln. Well, absolute u1 plus x squared, but that's positive anyway. So I can just write that. Plus 2c, but 2 times an arbitrary constant is not really different from a constant, so I just write c. It's a new c, right? It's 2c renamed as c. So that's fine. Now let's also find the value of c. We can do that by using the initial value. So y0 is equal to minus 2. So this tells us that minus 2 squared should be equal to 2 ln 1 plus 0 plus c. Here you have ln 1, so 0. And we deduce that c is equal to 4. So back to our equation, y squared is equal to 2 times ln 1 plus x squared plus 4. Now, we want to find y. Now, if its square is equal to that, it's either plus or minus the square root of this function. But which one is it? Both the plus and minus square root are possibilities. However, we have an initial value which is negative. So, it should be the minus one, so that it matches this initial value. Okay, that's good. We found it. Maybe as a side note, let's also note that the interval of definition of this solution is the whole real line, minus infinity to infinity. This is because any value of x makes the inside of the natural logarithm greater than 1. Therefore, the result of the natural logarithm is positive, and that's enough to make the inside of the square root positive. Okay. Now, let's solve one more example of this type, where I can say a couple of other things. Okay. This time, let's solve the following differential equation. dy dt equals y times y minus 2 times t. Now it's again multiplicatively separated, but maybe it's instructive to write this in the second form, like mt over ny. Let me note something important here. These two are equal, or this passage is a valid step if y is different from 0 or 2, because 0 and 2 make y times y minus 2 0. Therefore, in those cases, you cannot put this in the denominator. So in a sense, whatever I'll say for a while will be valid if y is different from 0 and 2. So when you are finished, you have to go back to y equals 0 and 2 and check them again. Okay, that being said, let's continue. Now multiply both sides by this denominator. So 1 over y times y minus 2 dy dt must be equal to t. Now we know the next step. We'll integrate both sides with respect to t. Okay, how do we integrate the left-hand side? Maybe let's remember a couple of things from calculus. This is a rational function. Therefore, the best way seems to be to use partial fractions. I want to find to real numbers a, b, which make this equation correct. So let's see. If I equate denominators, that gives a times y minus 2 plus b times y here. And if you want this to be correct for every value of y, then you need the coefficient of y to be equal to 0 and the constant, which is minus 2a, equals 1. So this gives you a equals minus 1 over 2, b equals 1 over 2. Okay, so the integral that we have dy over y times y minus 2 then becomes integral dy over y minus 2. I'm writing the b term first, plus the a term, but that's minus 1/2, so it will look like this. And on the right we had integral t dt. So I guess this is something we can do. The first integral, I'm sorry, so we have 2 here and 2 here. Now it's fine. Okay, the first integral is going to give you 1 over 2 ln absolute y minus 2. And the second integral will give 1 over 2 ln absolute y. The right hand side will be t squared over 2 plus c, where c is some constant. Now we can use a property of logarithm. We can take the 1 over 2 out, of course, and we have a difference of logarithms. That means division inside the logarithm. So we have this equality. Now I can get rid of the 2. T squared. It's harmless to replace 2c by c. Now we can exponentiate both sides. That's going to give us absolute y minus 2 over y equals e to the power t squared plus c. But notice that this is e to the t squared times e to the c. A sum on the top of an exponential becomes a product here. If I remove the absolute value, it's going to be y minus 2 over y equals either plus or minus e to the c times e to the t squared. Now this is equal to 1 minus 2 over y. So you probably see how I can solve for y from here. You could leave y alone. And there's also something here, plus or minus e to the c. That's complicated looking, but it's, again, a constant. Let me rename it as c. There's some annoying thing here when I rename this as c. Replacing 2c by c is completely harmless. But replacing plus or minus e to the c by c might raise the question, do we get the same set of constants? There's a gap here. Plus or minus e to the c might be anything except 0. So the c seems to be something different from 0. But we'll come back to that. Let me keep c for the moment. If you solve this, you can check that you get 2 divided by 1 minus c times e to the t squared. This part is simple arithmetic. You put the e to the c, e to the t squared on the left side, the other on the right side, and then divide. Now, this is fine. Let's go back to y equals 0 and y equals 2. So these were some values which we kept aside and which we said we should look at them once again. Now, y equals 0, the constant function, is that a solution of the differential equation? Well, plug it in the differential equation and check. So derivative of the 0 function, constant function, with respect to t, is that really equal to 0 times 0 minus 2 times t. This is the differential equation written for this particular function. And it's a correct equation. This derivative is 0, the right-hand side is 0, this holds. So y equals 0 is a solution. And the same type of thing happens for y equals 2. I mean, y equals the constant function 2. This is again 0, and on the right-hand side, you also get 0, as you see. So y equals 2 is also the solution. So if we are asked to write down all solutions, actually, we should say it's this, that, and that. So you have this infinite family of solutions depending on C, as well as y equals 0 and y equals 2. Now, let's come back to the question of C equals 0. If you put C equals 0, you get y equals 2. So actually, y equals 2 is a member of this family for that forgotten value of C. It's more difficult to interpret y equals 0 as part of this. It doesn't work for any C value. Maybe if you sort of stretch imagination and put C equals infinity, that could work. But okay, maybe it should be really written separately. So, but as a whole, these are all the solutions. Okay. The upshot is when you're solving, if you ever make a division, then you should be careful about possible lost solutions, and you should go back and check them later. Okay, so that kind of takes care of our discussion about separable equations. Now, let's put a twist to it. We want to make a substitution which turns a given equation to a separable equation. And I'll discuss sort of a class of examples. These are called homogeneous equations. So the idea is, this is again a special class, equations which are not separable, but which become separable after a substitution. But it's a little bit more than, it's a special substitution. Let me be more precise. So here's the definition. So you need a first order OD for what I'll say. So let's have an arbitrary first order equation. It's called separable if if this f dy can be rewritten in the form a function of y over t. Okay, such an f has to be really special. F is, in general, an arbitrary two-variable function, but h down here is a one-variable function, and that single variable is y over t. So only very, very special functions are of this form. Okay, for instance, dy dt equals t plus y is not of this type. It's not homogeneous. However, the second example is, let me tell you, test dy dt equals t plus y over t minus y. You might say, okay, in which sense is it of the form h of t or y over t? Well, you can rewrite it. You can divide both the numerator and the denominator by t, and it's the same thing. 1 plus y over t over 1 minus y over t. So setting h of v to be 1 plus v over 1 minus v, this right hand side is h of y over t, right? So even in the beginning, it may not immediately look like it. With a small manipulation, we see that it is homogeneous. Okay, so how do we solve these? Okay, now we have our homogeneous equation. Okay, we make a substitution. Substitutions were extremely useful in calculus, and they are also useful in differential equations. So let's say d equals y over t. Then, of course, y is equal to t times v. Now, when we make the substitution, of course, this is going to be h of v here, but it's also important to change the left-hand side. So we should look at dy dt, and we should try to write it in terms of this new variable v. So this is then taking the derivative of this product. And we know product rule from calculus. It's derivative of the first function times v plus t times derivative of the second function. dt is 1, so we have v plus t times dv dt. Now let's rewrite the original equation. Okay, the left side then becomes v plus t dv dt, and the right hand side is whatever function we have of v. Now, why is this any better than the original equation? Well, for the following thing. You can take this v on the right side, hv minus v. Then you could divide by hv minus v here and divide by t there. So you have following equality. Okay, I mean, the equation is separable now. It's separable. And we just solve it in the way we learn to solve separable equations. We integrate the two sides, then find v in terms of t if possible, and then substitute back v equals y over t. If leaving v alone is not possible, you might leave the solution in implicit form, which is also valuable. Okay, now let me actually work this out on an example. Okay, let's look at the following equation. dy dx. Okay, it's x instead of t, but it doesn't matter, of course. 3y squared minus x squared divided by 2 times x times y. Okay, it is homogeneous because I can write it like this. Divide both numerator and denominator by x squared. Okay, and of course I can rewrite this as 3y over x parenthesis squared minus 1 divided by 2 times y over x. So now everything on the right is in the form is a function of y over x, so that's good. So the equation is homogeneous, right? Okay, now let's follow the steps of solution. So let v equals y over x, then y equals xv, and by the product rule, let me not write the details here, dy dx is equal to v plus x dv dx. Okay, we should put this on the left side then. And rewrite the right side in terms of v. So this is now 3v squared minus 1 divided by 2v. And the whole point is this new equation should be separable. Okay, so x times dv dx equals 3v squared minus 1 over 2v minus v. We can simplify by equating denominators. This becomes, I guess, v squared minus 1 divided by 2v. Now put the v's on the left, x is on the right. And then integrate. Okay, if we say u equals v squared minus 1 here, then du equals 2v dv, which is above. So the left-hand side integral will just give you integral du over u, which is equal to ln absolute u. Let me write in terms of v. And the right side is ln absolute x. And I should put a plus c somewhere. Okay. Things went well so far. Now exponentiate both sides and on the left we just get rid of the ln. On the right, well, let me first write like this: ln absolute x plus c. But then again, since sum on top of an exponential becomes product, this is e to the ln x times e to the c. If we remove the absolute values on the left side, that's going to bring a plus minus here, e to the c again, and e to the ln absolute x is absolute x. Okay. Now you could rename this constant as c, as we have done before, and let's put v equals y over x back again. Something like that. Okay. Then y over x squared is 1 plus c times x. And you have y over x equal to 1 over, plus or minus square root 1 plus c times absolute x. This looks fine. So here, c could be any real number. Up here it was an exponential, so you might worry about c equals 0. I think we lost it on the way. Let's scroll back. So at some point in the derivation, I divided by b squared minus 1. So this step is assuming that b is not equal to plus or minus 1. So you should check b equals plus or minus 1 separately. Should be checked. But v is y over x, so this is y equals plus or minus x. These are solutions. You can substitute in the differential equation and check that they're solutions. Let me leave that to you. And in a sense, they kind of correspond to c equals 0 up here, because if you put c equals 0, you have 1, so that corresponds to y equals plus or minus x. So c equals 0 was not an actual problem. You can't take any real value. Okay, so today we discussed solving separable equations and combining it with a substitution to solve homogeneous equations, and that's all for this lecture. Thank you.